So here they will say improve the following principle of mathematical induction. So we have the first one by this. N plus 1 all over 6. So the first thing is to say let P of n be the statement 1 squared plus 2 squared plus 3 squared plus n squared all over 6. So we're going to check the left hand side and the right hand side. So on our left hand side, we have 1 squared which is equal to 1. Then the right hand side, it's equal to n 2 of n plus 1 n plus 1 all over 6. So we'll check for n equal to 1. Then you'll just have 2 1 plus 1. This will give us 2 times, this will give us 3 times 1 times 3 times 2 all over 6. And this is just 1. So we can clearly see that, okay, therefore the left hand side is equal to the right hand side. So the base case holds, or we can say it's true. So we come to the inductive. Sometimes you can say the assumption step. Same thing. So we're going to assume that P of n is true for n equal to k. Then from here, we're just going to take this, and then wherever you see n, we're going to replace with k. So meaning that this will be k squared and also there it will be having k. So now we can say that, remember we assumed that this is true on the assumption, assume that P of n is true for n equal to k, then you have this. Then we can come now and say use the deduction step. Use, we can deduce that P of n plus 1 let's just say deduce that P of n is true, is also true for some value of k, value of n equal to k plus 1. So we're going to replace we're going to include the next term. This will be k plus 1 all squared. And here we'll have k plus 1 into 2 into k plus 1 plus 1. Then here if we put k plus 1, this will be k plus 2. So let's reduce this. All over 6. So we can see that this will be 1 squared plus 2 squared being equal to k plus 1. This will give us 2k plus 3, k plus 2 all over 6. So now we're going to take the left hand side. Hopefully you can see that from here to here it's from the assumption. We said this is equal to this part. So we'll just copy it. Can allow me to put this here. But this is 2k plus 1, then plus k plus 1 all squared. And this will be, I can take out the common factor, which is k plus 1. I will be left with k, 2k plus 1, all over 6 plus k plus 1. So we can just simplify the inner function. I can take out 6 as our lowest common factor. You'll have k, 2k plus 1 plus 6k plus 6. When it multiplies there, then you'll have k plus 1 we're going to have k plus 1 into 2k squared plus k plus 6k plus 6 all over 6. And we can see that this is k plus 1. Then overall, this will be simplified to 2k squared plus 7k plus 6 all over 6. And hopefully you can see that on our right hand side, or we can just factorize this. Okay, so we're actually looking to get something like this. Searching for the right hand side. This is our right hand side. So here, if we write plus 3 plus 2 all over 6, you can see that this will give you back this one. Then therefore, we have managed to show that the right hand side is equal to the left hand side because they are equal. This is equal to the right hand side. Then the second one, letter B, So now coming to this part, then so we can say base case. Actually, before the base case, you're going to say let P of n be the statement is this. So now from here, we're going to check for the base case. So we're going to check for the first term. For the first term, we can see that the left hand side is equal to this. So 1 times 2 6 8 equal to n plus 1 n plus 2 n plus 3 all out of 4. Then for n equal to 1, you'll have 2, then this will be 3, 4, all over 4, and this is just 6. So you can clearly see that the left hand side is equal to the right hand side. Now, um, okay, so we can clearly see that the base case holds for letter B. Then we're gonna come to the assumption step. So on the assumption or inductive step, inductive or assumption, we're going to say assume that P of n is true for some value of n equal to k, such that, so come to our statement. Then here we'll just put k wherever you see n. Then now we can see that we can now go to the deduction step. So we're going to say deduce that P of n is also true for some value of n equal to k plus 1, such that then you'll just copy this. But now you are used to this, we know that this part, the whole of this part, it will be equal to that. So but I can first write it. And this will be k plus 1, k plus 2, and then this is equivalent to, then we'll say plus k plus, we say k plus 1 plus 1, it will be 2, then k plus 3, then it will be equivalent to, then we just put k plus 1 there. So this was gonna give us k plus 1, k plus 2, k plus 3, k plus 4, all over 4. So we know that will be having equal to that. I have to reduce this. So why having this? So and this part from the assumption is equal to that. So I'm just going to copy it. So we know that from assumption, this part is equal to this. Then we'll say plus k plus 2, k plus 3, all over 4. So in this case, you can allow me to take the left hand side alone, or we can write the right hand side first. So the right hand side will be equal to this, and I can take the left hand side, and we'll see what we can get. So this can be equal to NF plus k plus 2, k plus 3. So I'm going to take the common factor again, which is k plus 2 and k plus 3. Okay. So we'll remain with, and I think we forgot something here. From the assumption, we should be having k plus 1, k plus 2. I forgot that. So we must include it here. Okay. So, but, hence here we should be having we should be having k plus 1 as well. Remember that this part is k. Let me fix that mistake. This part is k. So when we put k plus 1, we should also be having k plus 1 here to come to the deduction step. So we should be having plus k plus 1. So it should be like that. So we took the left hand side, forgot to write due to that error. It means here we must fix it, and then we'll put the remaining k plus 1. So our common factor is also k plus 1. You'll put that there, and you'll be left with k with just k over 4 plus 1. Then we further simplify this. We're having k plus 1, k plus 2, k plus 3. You clearly see that we can also manipulate this to be that. So now if we simplify this, you'll get k plus 1, k plus 2, all over 4. And this is equal to the right hand side, which was that. So we can now go to letter B, letter C, and B. So you're given C, it's 1 over 2, 1 over 4. And they said 4, and it's greater or equal to 1. So in this case, it means we're not starting from n equal to 0, but n equal to 1. So you'll write your base case. Let Pn be the statement, and you write your base case. Obviously, you're going to say let n equal to 1. The left hand side will be equal to 1 over 2 to exponent n will be 1 over 2, 1, which is 1 over 2. Then our right hand side, we're having 1 minus 1 over 2n. You'll also substitute your 1. You'll get 1 over 2. So the left hand side is equal to the right hand side, and the base case hold to be true. Then we come to the next one, the next part, the induction step. So I'm going to say, assume that P of n is true for n equal to k. Then you are having 1 over 2 plus 1 over 4 plus 1 over 2k. We'll be having that from here. We just replace with k everywhere. Then we can now say that deduce, must now deduce the deduction step. So we can say deduce that P of n is also true for some value of n equal to k plus 1. So we already know we're having 1 over 2 plus 1 over 4. Then you'll add 1 over 2k plus 1. Here you just substitute k plus 1 directly. So you can take the left hand side and manipulate it. So we know that this part is equivalent to 1 minus 1 over 2k. So I having plus 1 over 2k plus 1. So here we can simplify this part. We will have what? 2k. This will be 2k minus 1 plus 1 over 2k plus 1. So I want us to take out the common factor 2k plus 1. This will be 2k minus 1 all over 2 to exponent negative 1 plus 1. Then if I simplify this, we should get 2k. We're gonna get 2k. This will give us 0 and plus 1. And if we simplify this, this will be plus 1. To simplify this, we're gonna get 2k plus 1 plus 2k plus 1. But we're looking for 1 minus. Okay, let me remove this and write it in another way. That will make this more simpler. I'll just remove up to there. So I could have said from okay, let's remove up here. I want to see. We could have grouped these two together, and then this will be 1 minus okay. This will be, if I group not these two, but let's group the ones that don't have a constant, these two. This will be all over 2k plus 1. This was going to give us 2 plus 1. And this is the same as 1 minus 2 over 2k plus 1 plus 1 over 2k plus 1. Right. So this will be 1 minus, we can agree that if I take this as a common factor, here you'll be left with 2 minus 1 due to this, that's negative there. Remember, it was not removed. So this will be 1 minus 1 over 2k plus 1. And this is equal to the right hand side. As I've said before, this requires some practice. Then let us see. This is for any positive, letter D, for any positive integer n, prove that n cubed plus 2n is always divisible by 3. 3. So you can say base can start, remember, I'm going to start by saying let P of n be the statement for any n cubed plus 2n is always divisible by 3. So we'll say base case. Then for n equal to 1, we know that the left-hand side, we're having n cubed plus 2n, which is 1 cubed plus 2, which is 3. Then our right, so we can see that 3 is divisible by 3. So it means the base case is true. Then we come to the inductive step or the assumption step. So here we're going to assume that P of n is true for n equal to k. Then recall that we were having something like this. So it means in our case we'll have this. Then we'll say this is equal to 3m, where m is an element of integers. Then we'll come to the deduction step. We want to deduce that for some P of n is also true for n equal to k plus 1. So we're going to have k plus 1 cube plus 2 into k plus 1. So if we expand this term, you'll get k cube plus 3k squared plus 3k plus 1 plus 2k plus 2. And this will be the same as k cube plus, so I'm going to group this with 2k. Then this one I'll group them together. 1 plus 2 will give us 3. So we can see that we're gonna have a multiple of 3. Remember that, recall that k cubed plus 2k will be equal to 3m. So you will replace that with 3m. Then I can take out 3, and then I have this remaining. With this an element of integers, then you'll have 3r. And I can say r is also an element of integers, such that r is equal to this. So we can see that this is a multiple of 3, therefore P of n is true for n equal for n being an element of what? Of integers. I've already shown how you conclude on the last class. So you will check how you can conclude better if this is not the way they are doing it in class. The letter E. So I actually wanted the ones that have factorial. So I'm gonna skip this one. The multiple of 13. You'll try that one only. Or maybe let me do it. You'll try letter E, letter F. So they are saying prove that the integer n greater than 0, you have this, is a multiple of 13. So we're having that. So I'm going to say base case when n is equal to 0, you will have 4 for n equal to 0. Then this will be 4 plus 3 to exponent 2. This will be 13. And therefore, the left-hand side is divisible by 13, right? So we can say, therefore, 13 is divisible. Or we can say is a multiple of 3 of 30. No matter they talked about multiple. Then now we'll come to the inductive step. So I'm going to assume that P of n is true for n equal to k. So you'll replace everywhere with k there. And this will be equal to 13m, where m is an element of integers. Then this will be 4 2k plus 1 is equal to 13m minus 3k plus 2. So this is actually true. Then we'll check for the deduction step. So we must deduce that for some value of n equal to n plus k plus 1, k of n is also true. Your p of k plus 1 is also true. So I'm going to say this is 2, this is going to be 2 into k plus 1 plus 1, k plus 1 plus 2. That this is just 13m for 2k plus 3. So remember, I want to show the multiple of let's go back. We want to show that okay. They say prove that for any integer n greater than is a multiple of 13. So we can say that from here we can say that I have 4 2k plus 1 plus 1 and plus 3k plus 3. Then I leave this on the left. You can clearly see that this is the same as 4 2k plus what? So remember checking for plus 2 plus 1 3k plus 3. This will just be 4 2k plus 3 plus 3k plus 3. And this will be the same as 4 to exponent 2 4 2k plus 1. So this is the same as that plus 3 times 3k plus 2. This will be 16 you'll have that. Then I can say, remember we still have our 13M. So I can say that I can take out 16. If I take out 16, 2k plus 1 is equal to something from the assumption is equal to this. So you must be very, very observant. So I'm going to replace it in red. It's 13M minus 3k plus 2. Then you must write a reason when you're where are you finding that? So here we can see that I am going to replace this guy with, but before that you must say from the assumption. Write your reason. Then we're going to come here, and we're going to say this is equal to 16, 13M. When you simplify, you have this. K plus 2. So now I can actually take out 13. But before we do that, remember here we have this 16. Let's check. 13 initial from the assumption it's equal to 4 2k plus 1 plus 3k plus 2. This is 13M. Just want us to check on this part. Okay, we can now say that this is going to be minus by having minus this part here is going to be minus 13, having 13 times 3k plus 2. Then from here we can factorize 13. Yeah, then therefore this is 13. We can let this to be r, where r is an element of integers. And this seems, it shows that it's a multiple. We are having a multiple of 13. Therefore we have a multiple of 13. So you conclude by saying therefore P of n is true for all n values being an element of integers by the principle, you'd say by the principle of mathematical induction. This is true. So let's see the next one. So now I'm gonna take letter F. Okay, I'm gonna skip F. I want to take letter G and H. If one. So this is what we're having. So we're going to say base case. We can start by saying let P of n be the statement. Then we can now have the base case. The right hand side will be 4 factorial, and this will be 4 times 3 times 2 times 1, which is 24. So and this is true. The right must be greater than the left. So I'm going to say 16 is indeed less than 24. Therefore, the base case holds. Then we'll come to the inductive step. So we'll say assume that P of n is true for n equal to k, where k is greater or equal to 4. Then you have 2k less than k factorial. Then for n equal to k plus 1 on the deduction step, you're going to have this. You'll have 2k plus 1 is less than k plus 1 factorial. Then this will be 2k plus 1 is less than, let's see. Okay, we can separate this on this step. We will have 2k times 2. And we know that this can be written as k plus 1, k plus 1, k factorial. Then since k is greater or equal to 4, it will be true. Remember, let's take the assumption step. From the assumption step, we are having this. So to exponent k is less than that. We have already proven that that is true. So now if here I multiply both sides by 2, this will still remain true. You see there. So it means that even if I have 2 only, it will be less than k plus 1. And also if I have 2 k factorial, I multiply both sides by k factorial, I'll have less than k plus 1 k factorial. I'll still have a less than there. Again, then this means that we know that this part is equivalent to k plus 1 factorial. We're still having 2k factorial. This implies that when you have 2k plus 1, it will still be less than k plus 1 factorial. So this is based on inequality laws. Once you understand them, you won't suffer from these factorial things. Then now we'll come to the last one. They are saying when you have h5n less than n plus 5 for all n greater or equal to 1, this is going to be number 5. Okay, the last one, letter H. So we can say that we have the base case. So you can allow me to say the left-hand side here would be equal to 5 to exponent n, which is 5 to exponent 1. We're checking for n equal to 1, and then this is just 5. Then we can also check the right hand side. It will be given by n plus 5 factorial, which will be 6 factorial. This is 720. And 720 is indeed greater than that. So this is true. 5 is greater, 720 is greater than 5. So the base case holds. Then I'll come to the inductive step. You can say assume that P of n is true for some, okay, let's just say for n equal to k, where k is greater or equal to 1, or starting at 1. This inequality is very important. So we're having 5k being less than n plus 5. Initially we're having this. So this will be k plus 5 factorial. Then we'll come to the reduction step. So you must deduce that P of n is also true for some for some value of n being equal to k plus 1, where k is an element of integers. So we can agree that I will have 5k plus 1 is less than k plus 6 factorial. And then we can have 5 times 5k being less than k plus 6. So if I apply by the assumption or by the inductive hypothesis, so we want to apply the laws of inequalities. We know that if I multiply this side by 5, this will always, the right hand side will always be bigger. You can even check with numbers. This is 7 factorial times 5. This is just 25. You see that this is still, it will still be big. So we can now say that this will imply that 5 of k plus 5 factorial will be less than k plus 6, k plus 5 factorial. When I simplify that, then this will imply that 5k plus 1 will be less than k plus 6. We'll also try to find a better way you can write this. I think I can stop the recording here. Let's try to take this one. Skipped one question. I think we can do it. Still have time. Verify that this is true for all natural numbers. Letter F. So we're having this. So obviously we have the base case 2 to exponent 1. They say it's an element of natural numbers. It means n is equal to 1. We're gonna start at n equal to 1. So this will be 2 on the left hand side. Then the right hand side you'll have 1 squared. So this is true. So the base case, let's say the base case holds. Then we can now say by the inductive hypothesis or the inductive step, basically you will have what 2k is greater than k squared. Then deduce. So yeah, I'm skipping those steps. So for the deduction part, you can say f 2k plus 1 greater than k plus 1 all squared. If I expand the left hand side, then here we are having k plus 1 all squared. Someone can even further simplify this. It's not a problem. The main part is to deduce that this will always be true. So by hypothesis or from the assumption step, we know that we assumed that 2k must be greater than 2k squared, or we said k squared, but even if multiplied by 2 both sides, né? Even if we multiply by 2 both sides, it still holds, long as it's an equivalent constant. So we can say that I can have k plus 1 we know that in a case of, yeah, I think I can even write it like this. We know that we're having this. So if I multiply both sides here by 2 and 2, this will be 2k squared plus 4k plus 1. This is just 2 to exponent k plus 3. So this is an exponential, this is a quadratic. So this is growing faster. So we can see that by the principle of mathematical induction, P of n is true for all n values being an element of natural numbers.